Okay, so I wanted to do a video for people that are struggling with the vector components and to go over a few other things with you guys that I think will make this a little easier. If you got it figured out really well, then don't worry about this. Keep doing what you're doing. If you're having trouble, then I'm going to show you another way of looking at these that might be easier for you. And as we move on to a type of problem in a day or two that's going to build on the ones we've been doing and kind of combine those two types of problems, you might want to pick the easiest way to do these components for you because it'll make those harder problems easier. So basically, first what I want to go over with you is if we're talking about angles, about complementary angles. If I notice right here, this vector is at 0 degrees, and if I rotate it counterclockwise, I first go up, and that is 10 degrees north of east, but it's also a complementary angle of that is 8 degrees east of north. Both of those would be ways of describing that vector of what direction that it's going. And then if I keep going around, it'll be 20 degrees north of east or 70 degrees east of north. And then if you notice, it's showing my x and y components. My x component is in pink there, and the y component is in green, although it's not showing them tip to tail, but it's still showing what they are. And remember, this vector right here is going in the northeast direction, and if it was a displacement vector, that person would be displacing so much to the east and so much to the north also, since they're moving northeast. They got a north component and an east component, or what we call an x and y component of their displacement. Now if I keep rotating it, if you notice I get to the y-axis there, I get to 90 degrees, and if you notice I don't have an x component. My y component is just the whatever length of the vector, which in this case is 120, and so when I'm at 0 degrees I would have no y component. And if I keep going now, as I move, I'm 10 degrees west of north, but I'm also 80 degrees north of west, because that's 90 degrees in between west and north. And then I keep going, I get to 40 degrees west and north is the same thing as 50 degrees north of west. And if you notice, I get to right here, I get to due west. My s component is this negative 120, the length of the vector. I have no y component. And then if you keep going in this quadrant, it's the same thing. I get here to I'm going due south, my y component is negative, my s component is 0, and then I'll come back around. Like I said, these are all complementary angles. If I ask you, you got 40 degrees east to south, what's the complementary angle of that? You would tell me 50 degrees south of east. And then I come back around to there, 0 degrees, which would have a y-x component since the length of the vector. The y component would be 0 because you're not displacing or moving at a speed that is that has a y component to it. You're moving due east. Now, if we look at this from another perspective, we look at it from an angle. There's another way we can measure angles, and it is counterclockwise from the positive x-axis. So this is kind of a standard way of measuring it. If you look at what's in green up there, it says 0 degrees. And if I move up, now I'm 10 degrees, 20, 30, 40, 50, 60, 70, 80, 90. And I'm at 90 degrees, then I move on and I'm at 100 degrees, 110, 120, and so forth till I get to 180, which would be due west. And then I could keep going till I get to due south, which is 270, and I can keep going. And say if I got here at 300 degrees, measuring from the positive x counterclockwise, well, measuring it clockwise, we would be negative numbers, it would be negative 60, but we're not worried about that. I want you to worry about the counterclockwise from the positive x-axis, knowing that if you had this vector right here, you could measure it 300 degrees. Now, what would that be? If we went back to, this is 270, and if we moved over to 280 degrees, another way we could show that would be, 10 degrees east of south, or 80 degrees south of east. Those are, three different ways we could describe that angle right there. But, and I didn't really know teach these components every year. I'm going to show you a different way of doing it using the counterclockwise angle that I think might be a little easier for some of you. But students, I've noticed over the years do these differently. Some like to use the trig, where they make the triangle and learn what they used in math, and some like to use the other way that I teach it. So you can just kind of pick which one's easier for you. Now, if we look at vectors and what are we trying to do, first of all, if I pick a vector and I put it at the origin, and let's extend it out, so it's at 14.1, or let's just start it here at 15. All right, if you notice at the top, it tells me the length of my vector is 15. We can say meters per second, it doesn't really matter but the units. And if you notice, the angle's at 0, and my x component is 15, my y component is 0. And if I start to move up, so I move up to somewhere along here, and if I had a vector that is 14.2 meters long, and this is at 39.3 degrees, and my x component is 11, my y component would be 9. Now if I put my components in here, if you notice I draw my components, my x component is drawn along the x-axis, and it's pointing in this case to the east. It's got an eastern component and it's positive. The y component is positive, pointing in the northern direction, and I draw them tip to tail. So when I break down a vector, I draw the x and y component. That way I can tell, and I know in this case they're both positive. If I keep moving around, if you notice as I move closer to the y-axis, my y component gets bigger, my x component gets smaller. Let's say I get to right here, and this is at 90 degrees. I have no x component, my y component is just the length of the vector. Alright, now if I keep going like this, and it's going to tell me my angle's at 108. If you notice when I get to this quadrant that my x is negative, my y is positive. If I keep going, keep closer to the x-axis, my x component's going to get bigger, my y component's going to get smaller. And then I get over here to 180 degrees, and it's telling me that my x component is negative 16 because it's pointing towards the west. And if I don't get the sign right, I miss the problem. I think that's where a lot of people might mess up, is they don't get their signs right. That's why I'm going to show you another method today where you don't have to worry about finding your signs, because it's going to give you the correct sign. Alright, but if I keep going and I get in this quadrant, if you notice that this vector now is pointing in the southwestern direction, and my x component would be negative 12, my y component is negative also. So in the third quadrant, if that vector is there, then it's going to be both are going to be negative. And if I keep going, and it's giving me my angles negatively, I'm going back through here, but that would be, if I'll start at 180, I could keep on adding. It's just giving me negative all the way back down to 0. And if I get to due south, then I only have a y component. If you look at the top, negative 12, my x component is 0. And that's just, some of the vector that's due south. And as I go towards this in the fourth quadrant, if you notice, my vector has a positive x and a negative y, all the way back down to 0 degrees. Now, first we talk about complementary angles. How could I describe this angle right here two different ways? Well, the way I would do that first is this angle is in between, this is east, and this is north. So it's 20 degrees. If I'm starting right here at the east and going here, I'm going north from east, so it's 20 degrees north from east or north of east. Or if I look at it from the other direction, I have to go 80 degrees east from north. That's another way of describing that. Now you're going to want to pause this video and copy down some of these notes as you get to a point where you want to write down an example problem or need to slow down. Alright, this way, another way of describing this angle, if I was going to describe, would be if I am, this is west and this is south. Well, if I'm right here and I'm going to the vector, I got to go 60 degrees and then I have to go south from west. Or the opposite would be, that would have to be, the difference between 60 and 90, which would be 30 degrees west from south. Two different ways to show the same angle, and I'll ask you that on the test when we have one. Now I want to look at the angle counterclockwise from the x-axis. Alright, if you see CCW, that always means counterclockwise from the positive x, meaning I want to measure that angle. If you notice, this angle is 10 degrees west from north, but I want to measure it from the positive x all the way till I get here. And what would that be? Well, from here to here is 90. So from here to here is 10. So that would just be 90 plus 10. That would be 100 degrees. That's counterclockwise. If I have this example right here, 70 degrees, that's 70 degrees west from south. But I want to measure it from here all the way to here. Well, I know when I get to right here, that's 180. And then if I go all the way to here, that is 270. And the best way to find this angle would just be to take 270 and minus 70, and that would give you 200. That's 200 from here to here. Another thing you could have did was found that this angle right here had to be 20, and then took 180 plus 20, which would have been 200. Either way, you'd have got 200. And the last one, if I had 20 degrees, this right here, how could I find it from the positive x all the way around till I touch this? Well, I could either I know that all the way around back to here would be 360. So I took 360 minus 20. I would have 340. That would be the way of describing it. I also could have said, well, from here to here is 270, and then this right here has to be 70 degrees. And then you could have just took 270 plus 70, and that would give you 340. Either way, you find that angle counterclockwise from the positive x would be 340 degrees. Now that's important because if you choose this new way of working vector components, you're going to have to measure your angle from counterclockwise from the positive x-axis. And that's the way that I normally teach this, but I noticed that so many kids over the years working problems using the trig, using the angle that was given to them in the problem, that I decided to teach it a different way. But now, when you do that, you have to be very conscious of your signs of your x and y when you calculate it to make them negative or positive if they need to be. So either way, there's drawbacks to it. So I'm going to show you both ways and let you pick which way that you want to do these problems. Just know that whenever you see me work out the solutions in a worksheet, I might do it just one way, work the solutions out. And it might not go exactly the way you do it, but you can figure out what you did wrong, and you'll be able to figure it out even if you work them out differently than what I do. Now, first, if we talk about vector components, this is the problem with doing it by the angle that you're given in the problem. All right, so let's look just at vector A. Don't look at vector B, what's in blue, or vector B, just at vector A. Alright, at vector A, if if I was going to find the x and y components, I know that sine of theta is opposite over the hypotenuse. Cosine is always adjacent over hypotenuse. Well, it kind of gets aggravating going through those equations like that all the time where I can shorten them up. I know in this case, in vector A, I've drawn out what A of x, where A of x goes. Right there, I'm drawing A of y, and that makes a right angle there. And because they're at right angles, we can, figure out what the legs are if we're given the hypotenuse and the angle, or if we're given AX and AY, we can figure out the resultant A and the angle. Either way, so problems we worked, we just did the reverse of the two kinds of problems. So, sine's also always associated with opposite, cosine's always associated with adjacent. So I'm going to kind of shorten this up. If I want to solve for, and I write this, the vector, I label it as A. And that's why components AX and AY. So if I want to find AX, instead of going through this stuff up here, I know that X is adjacent to the angle, and adjacent is cosine, so it's going to be the length of the vector, which is the hypotenuse, times the cosine of the angle. And I know that AY in this example, its opposite, is going to be times the sine of the angle. If I was working this out. But the problem is, if I look at this next example, if I look at B, it's going to be right the opposite. If I'm given the angle that's in between that is like west of north, if I'm given that angle in between the y-axis and the vector, it does exactly the opposite. So if I was going to find, let's say, this is vector B, so I'm going to find Bx. That would be the length of B times now X is opposite of the angle, so I would have to use sine in this case. And By would be B, and since Y is adjacent to the angle, I would use cosine of the angle. So if you notice, these are right the opposite, and that might get confusing. Is there a way that I can make it where the X component is always cosine or sine, the Y component is always cosine or sine? Yes, there is, but I have to measure my angle counterclockwise from the positive x-axis for that to work, and I'll show you in just a second how that is. Now, first example, I'm going to work the way that I've been working them and the way you've been working them so far. So if this works for you, keep doing this. Don't change unless you just see that the other way is easier and you'd like to do it that way. I'm going to show you the old way first. Now, if I want to draw, first I got to do is it's 96 meters per second at 7 degrees west from north. I have to know when I draw this that, this is north. I got to go 7 degrees towards the west. So it's this angle here. It's not the angle in between the negative x and the vector. Because if you do draw it wrong, you're going to miss the problem. You're going to get your components wrong. So you have to be very careful. So I'm going to draw my x and y components first. I notice that this velocity is moving at a northwestern direction. He's going to have a western component, which is an x component, and he's going to have a northern component, which is his y component. So I draw that, and I'm going to label this vector. We'll label A, but it is 96 meters per second. And then, so I'm going to label this as my AX. And I can't draw very straight, but so I'm going to put graph paper on here where I can draw straighter lines, and it still don't work. And this is AY. And I just drew that wrong. I need to redo that. this would be, I need to label this, and I would need to draw my, that would be my A of Y, that would be my AX, and that makes a right triangle. If I would have drew it the other way, I would have had to have used, the way I first drew it, I would have had not be able to use 7 degrees, I would have had to use 90 minus 7, which would have been 83 degrees, which I could have done, it would have worked out fine, but I draw it like this. Alright, so I'm going to solve for my X and Y components. First, I'm going to do my AX. I notice that my X component is always equal to A times the cosine, or not, in this case, it's going to be equal to A times the, and AX is opposite, so it's going to be sine of the angle, or, you know, if I put in my numbers, it's going to be 96 times the sine of 7 degrees, which would give me negative 11.7, and it's meters per second. And then if I was going to find my Y component, my Y component is adjacent, and if it's adjacent, I use cosine. So that's going to be whatever the length of A is times the cosine of the angle, which is 96 times the cosine of 7 degrees, which equals, and AY is equals 95.3 meters per second. Now if you notice when I did this problem, when I did this, I actually didn't get negative when I put in my calculator. I had to go back and look and see that I had negative AX there and go in and put that in there, negative AX, and I think that's the problem some people have, is checking that and going back and looking at that. There is one way you can fix that though. If you notice that your vector is in this direction, that you're going to have a negative X from the beginning, then you could always put negative in there, negative 96 times the sine of 7 degrees, you know, and then for AY you wouldn't want to do that. You'd want to leave it at 96. You just notice that your X is negative from the beginning. But, you know, if that works for you, doing it like this, keep on doing it like this, I wouldn't change anything. However, I'm going to show you another way to work the same problem. Alright, if you measure the angle counterclockwise from the positive x-axis, then cosine is always used for the x component and sine is always used for the y component. This will also give you the correct sign, positive or negative, of the components, so you wouldn't have to worry about the sign at all. You know, it would give you the correct sign. You wouldn't have to go back and check it. That way, you just have to remember, measure your angle from the counterclockwise, from the positive x-axis, always. And these will be your equations. You can always use those. You can write them down. You won't have to figure out what's adjacent, what's opposite. You know, you can always use this right here. Like I said, pause this video, write this down if you need to. Now I'm going to work the same problem using this method right here. I've already, 7 degrees west from north. I drew my vector. I drew my y component, my x component. And then I'm going to use my equations. My first one said AX is equal to A, which in this case is 96. A times the cosine of theta. Now theta is what I got to figure out. I got to measure my angle from counterclockwise. So if I'm going to do that, I got to measure from here all the way till that touches. That would be from here to here would be 90. 90 plus 7, I'd have to use 97 degrees for this to work. And when I do that, AX equals 96 times the cosine of 97 degrees. That will give you negative 11.7 meters per second for your X component. You don't even have to worry about the sign. You just have to remember to change your angle from the beginning. And then if I do the Y component, Y is going to be equal to A times the sine. Remember, sine always goes with the Y component. If you're using this method, cosine always goes with the X component. The angle, so that's going to be 96 times the sine of 97 degrees. And that will give you positive 95.3 meters per second for your Y component. And so that method might be easier for you, and especially if you're having trouble understanding this, I think this one will be better. This is normally the way I teach it, but I know so many students like to do it the other way that, I'll leave it up to you, showing you both ways. One more problem. If I have a vector that's 11 kilometers at 57 degrees south from west, and I'm saying this vector is B, it doesn't matter if I label it A, B, C, or whatever, but I draw that. Remember, it's 57 degrees south and west. I gotta go 57 degrees towards the south to get there, and I draw my vector. Alright, and it's 11 kilometers, and I'm gonna label it this vector B. So my X component this is what I'm going to call BX, and then down, this I'm calling BY, makes a right triangle right there. Now, before I even start, I need to measure this angle from here all the way to right here. Well, from here to here is going to be 180. And then I have to go 57 more degrees, so that'd be plus 57. Be 237 degrees is what I need to use. So then I go back, have my equations. If I have, this case I'm solving for bx, that's going to equal whatever the length of b is, times the cosine of the angle, always cosine if I'm using the counterclockwise from the positive x-axis. So when I plug that in, that's going to be 11 times the cosine of 237 degrees, and that's 11 times the cosine of that, and that would give you negative 6 kilometers for your x. And then for your y, by equals b times the sine of the angle. So that's going to be 11 times the sine of 237. And when you work that out, you will get negative 9.2 kilometers. And you can always check it to see if it makes sense. The vector's in the third quadrant, so it should have a negative x and a negative y, and you got that in your answers. And also, the vector is closer to the y-axis, meaning this angle here is shorter than 57 degrees. If it's closer to the y-axis, then my y component should be bigger, and it is. It's larger than my x. That's one way you can check these to make sure you get them right. And always double check things because this is easy to mess up. When we move on to the next type of problem, we're going to be combining, breaking down components and finding the resultant. And if you don't have a good understanding about this, you're going to struggle with that. So, I hope this helps.